Equilibrium. It looks so peaceful, but you know that's not it. The air molecules are colliding at 1,000 miles per hour, and water molecules at twice that. It looks more like this, except that gas molecules don't actually fly around like ping-pong balls. Molecular nitrogen and oxygen exhibit wave-particle duality, so their momentum and position spread like waves between collisions. At equilibrium, it looks like nothing is happening, but actually everything that can possibly happen is happening at the same time, just completely randomly. There are two ideas packed into randomness. One is unpredictability, but a predictable kind of unpredictability. And the other is an even distribution of unevenness. All the possibilities are evenly distributed over space and time, so there is no discrete information here. There are no waves or identifiable distinctions. It is every possibility all at once. It's incomprehensible, but it has a shape and a feel, and the randomness is critical to the production of clean information. At equilibrium, a body is primed to receive, conduct, or transmit information. The further away a body is from equilibrium, the more noise it will introduce, and the worse it is as an information system. It is also really bad for an airplane trying to land. Powder snow is a perfectly random distribution of snow and air. The great sense of freedom you get from skiing powder is that you can take any line you want, or just let your skis fly. Your path is random, whereas moguls present you with a well-defined path. It's the difference between exploring and solving puzzles. They're both fun, but in different ways. The point is not to know equilibrium, or even to understand it. The point is to appreciate it, and maybe try to protect it. If you don't protect the silence, the stillness, and all the other kinds of random equilibrium, you will find yourself unable to communicate. This is not to say that what is knowable is insignificant. It's incredibly useful. But compared to what is real, what is knowable isn't even small. Infinity buffs will appreciate that if you take the Shannon measure of information and let the number of possibilities increase to the infinite set of real numbers, s is equal to the log base 2 of the continuum, so that 2 to the power of s equals r. This means that s, the measure of information in the continuum, equals Aleph null, and more generally that the information that can be derived from the infinity of the continuum is equal to the infinity of natural numbers. This may not be important, but it has two correlations. First, a model of the real could only run on an infinitely powerful computer. Second, the measure of information derived from the real is infinite, but that information is still infinitely smaller than the real itself. This goes a long way to explaining why quantum mechanics and relativity can't be mapped one onto the other. One is quantized, as the name suggests, and therefore limited by countability, while the other is continuous and unable to distinguish between discrete values. Whatever it means, equilibrium gives us a glimpse of the infinite and a taste of the continuum.